Hello again. I wanted to do a few optimization problems. So these optimization problems are like the related rates problem. First, you have to set up an equation. Once you get an equation where some quantity is described in terms of another, then you can apply derivatives or whatever to get your answer. So let's do number 17 in section 3.7. This is pretty much classic optimization problem. You have a rectangular storage container, and okay, so we've got a rectangular storage container. It's good, always good to draw a picture. Helps you think about it. Okay, there's our rectangular storage container. The length of it's supposed to have a volume of 10 cubic meters. So we know the volume is 10 cubic meters, okay? It also says the length of its base is twice the width. So if we let this be x, this has to be 2x, okay? And let's label height h. It's beginning to look a little bit like the other problem. There is a twist though. Material for the base costs $10 per square meter. So the material for the base is $10 per square meter. Okay. The material for the sides costs $6 per square meter. Okay. Material, okay, find the cost of materials for the cheapest such container. So, and also in problem 17, we're going to put a lid on it that's made from the same material as the sides. Okay, so now, a lot of times that what you need to do is in the last sentence of these problems. Find the cost of materials for the cheapest such container. So you need, what do you need to minimize or maximize? You need to minimize cost. So somehow we need to write cost as a function of how much materials we need to use. Okay, so what would the cost be? Okay, so let's see, the cost would be equal to the cost of the base. The area of the base is 2x squared, right? X times 2x times $10 per square meter. That's the cost of the base. Okay, let's see. The cost of the lid is just $6 per square meter, but the lid is going to have the same area, but it's going to be $6 per square meter. Okay, so now we need the sides. Well, this side and the opposite side, so there's two of them, are x times h, right? The area of this side is x times h. The area of the opposite side is x times h. So there'll be two of them, and they're $6 per meter squared. And now we need the area of this side and that opposite side, so it would be 2x times h, right? Let me move this over. Okay, so this term was this side plus the opposite side at $6 per meter squared. Now this side is 2xh, but there's two of them, so that's 4xh times $6. Okay, so now let's multiply things out. This is 20x squared This is 12x squared, so this is going to be 32x squared. Then this part is going to be 12xh plus 24xh, which is going to be 36xh. Okay, this is typical in these problems. Our issue is we have cost as a function of two different variables, x and h. But fortunately, we have another bit of information that we haven't used. The volume has to be 10 meters cubed. So over here, I'm going to do this. I'm going to say the volume would be the area of the base times the height. So it would be 2x squared h. And we know that's supposed to be 10. So now we can get h in terms of x. So I divide both sides by 2x squared. I can do this because x can't be 0. If x is 0, there is no box. So we get h has got to be 5 over x squared, so I can put that in here. Okay. So, 5 over x squared, sorry. Okay. So now we can cancel one of these x's down here with that, right? So what we're going to have is 36 times 5 over x. All right? What's 36 times 5? I need my calculator. I'm going to use my calculator. 36 times 5 is 180. Okay, so I can rewrite this as 180 over x. Okay, now we're in shape. Now we need to know where the minimum is for this. Now, really we should think about what can x be? X can be anything bigger than 0, right? So we want to get the smallest possible cost. We need to figure out what x has to be to get the smallest possible cost. Once we get x, then we can get h, so we know exactly what we're building. But notice the problem says find the cost for the cheapest such container. Okay, so we've got to find the derivative. C prime of x equals 64x. Then this is going to be 180 times x to the negative 1. So we can just bring the negative 1 down and decrease the exponent by 1. That'll give us an x to the negative 2, which is x squared. Where could that be a minimum? Where the derivative is 0. Okay, so I'm going to get rid of this and get some room up here. So I'm going to set this to 0. Okay, so I'd have 180 over x squared equals 64x. Multiply both sides by x squared, divide by 64, and we'd have that. Okay, so how do we get x? We take the cube root of 180 over 64. So I'm going to do that on the calculator. 180 over 64 to the 1/3. And I get, let's say, 1.412. Let's say we do 3 decimal places. So it looks like if x is 1.412 meters, it looks like we'll have, that could possibly be a minimum, a local minimum. But how can we check? Well, to make sure it's a minimum and not a maximum, I'll leave this up here. To make sure it's a minimum and not a maximum, we could get the second derivative. So if we get the second derivative, that's going to be, let me write it up here. It's going to be 64. Derivative of 64x is 64. Then we're going to have a minus 2 come down, right? 180 over x cubed. So we're going to have 64 plus 2 times 180. What is that? 360 over x cubed. That's the second derivative. Well, if I put this number into here, my second derivative is positive. So that means the function is concave up. That means this is a local minimum. Okay, so we can say, let's see. Well, we don't want 0, right? We don't want 0. So we know that this function, too, for all the values of x greater than 0 is concave up. So this must be a minimum. Okay, so now we still have to answer the question. What we've got to do is put in 1.412 into the original function. And when we put 1.412 into the original function, what we get is $191.28. So that's the minimum cost. That's problem 17. You're going to have to do problem 16, which is just like it, little twist. Problem 18 and problem 19. Again, they're all just like it. There's just a little bit of a twist to it. See you soon.